In the previous learning sequence, we discussed how to use covariance and correlation to estimate, to assess a linear relationship between two numeric variables, right? And then in many plots, when we made the scatter plots, where one variable is shown against the other variable, we fitted these points with a straight line. But we didn't discuss how to make this fit, and that's actually what the second learning sequence is about, how to make a linear fit and what benefits you can get out of it. So that's what we call a simple linear regression. But let's start with defining what actually regression is. Well, if you think about correlation analysis, you remember, for example, for this people data, we tried every variable with any other variable, right? So we kind of treat all the variables equally and analyzed all different combinations, all different pairwise combinations of them. But in regression, we kind of split the variables into two groups. One variable is what we want to predict, and one variable is what we want to measure directly. So that's the overall idea. You measure something directly, and then you predict one or two or several variables by using these direct measurements. And that's what we call regression. So you regress y on x, so to speak. Usually regression is just, it's a mathematical function. It can be anything. In this learning sequence, we will discuss mostly the linear function, but in fact, it can be anything. You can use exponential, you can use logarithmic regression. It depends what relationship your data actually follows. And then y is a function of f, where function can be anything. This is the x variables, and then these are the parameters of this function. And that's actually the overall idea of the regression, to find these parameters so the fit is best possible. However, there are many questions still. For example, which function we should use? How to find out that one function is better than the other one? How to find actually these model parameters that makes the fit the best possible? And what actually is the best fit? How in general evaluate the quality of your regression model? So that's exactly what we are going to talk in this learning sequence. But why you need regression? Why just not to use correlation and covariance? Well, regression has two objectives. First of all, regression provides you how predictors influence the response. You see, now we have two new terms, predictors and response. Predictors is what you measure, and response is what you predict with your model, right? Later in the third learning sequence, you will learn how to make a regression when you have several x variables. In this learning sequence, we will use only one, but still, nevertheless, so the regression will tell you how x affects the y. So you can say you estimate an effect of what happens to y if you change x. So in this case, regression is very similar to one-way ANOVA, or at least simple linear regression is very similar to one-way ANOVA, except that in case of regression, both x and y are numeric, while in one-way ANOVA, x should be either qualitative or discrete variable, right? And the second is that it indeed led you to predict the response. So instead of measuring y directly, you can predict it by measuring something else. For example, instead of, if you don't have scale, you can measure height of person and predict his or her weight without actually measuring the weight directly. And this example maybe is not the best one because it's easy to measure both height and weight, but sometimes there are some properties that you cannot measure, or it's difficult to measure. For example, in spectroscopy, you measure absorbance of light and then you predict concentration. Of course, measuring absorbance of light is much easier than measure concentration of chemicals directly. Okay. So two reasons. First, that you can find how x influence of y, so you can find an effect of x on y. And second, you can predict y indirectly without measuring y directly. Right. So all in all, regression assumes that you have two sets of variables, x and y. We call x predictors and y we call response. Then the process of making this model, right, the process of finding the optimal parameter of your model is called training, fitting, or calibration in different areas. For example, in statistics, we mostly use fitting. In data science, people use training. In chemistry, for example, in chemometrics, people use calibration. But all these three terms have the same meaning. It's a process of creating a regression model. It's a process of finding parameters that makes the fit the best. Okay. And then when you have the model, you can make the predictions. So it means that you can apply this model to something new. So you measure x, but you didn't measure y, and then you can predict y. So that's what we call prediction. Okay. And this is just another example where I use many x variables. Imagine that you want to sell a house. you know that this house is from Svenstrup. It has 160 square meters area of the house, 5 rooms, 800 square meters outside. It was built in 1981 and renovated in 2008. How much will it cost? So all these are x variables. So this is x1, this is x2, this is x3, x4, and then x5, and then x6, right? And then this one, how much it costs, it's a y. So this is what you want to predict. In this case, we have a situation where you cannot measure y. It's not possible to look at the house and say how much does it cost, right? You need to, the only way to find the price, to estimate the price, is to make this prediction, is to make the regression model. Well, how to make it? Well, first of all, usually the regression model is created, is fitted based on data where you have both x and y known. So it means that you need information about houses, for example, 1,000 houses or less, maybe 100 houses or 10 houses that were sold in this city area in Svenstrup, for example, the last couple of years. And then you train this model, you find these coefficients, and then it let you predict the price of the house. So that's the first outcome, and that's the main outcome in this case. And the second also, it shows you how every x variable, so x1, x2, x3, x4, x5, and so on, influence the price. For example, how much 1 square meter costs, or how much it will cost if you add one more room, or how much it will cost if you, for example, renovate it again. So every variable, every x variable has an effect on the price, and that's what also the linear regression provides you. Okay, so this is the idea. Now, this is schematic illustration of these two processes. So for training, you need a training set. You need a set of x and y variables with known values. And then you use this set to make a model, to get a model, to train, to feed, to calibrate the model. And then when you have the model, you measure only x, you don't need y in this case, and then you use model to predict y. So that's the prediction, and this is the training. Okay. I already defined the x variables as predictors and y variables as responses. Sometimes we also call x variables as independent and y variables dependent, meaning that x variables do not influence each other, they vary independently, while y variable depends on the x. Okay. And then if both x and y include only one variable, so for example, you predict weight by knowing height of person, or you predict concentration by knowing absorbance of light at particular wavelengths, then what is called univariate regression or simple regression. But if x has many variables, like in this example with houses, then it's a multivariate regression. In this learning sequence, we will be talking about univariate regression, and then in the next and the third learning sequence of this block, we will talk about the multivariate regression. So that was a little intro, and in the next video, we will talk about simple linear regression in more detail.